It all started over lunch. In the summer of 1950, at the Los Alamos National Laboratory, the physicist Enrico Fermi was walking to a meal with his colleagues. They were chatting about recent UFO reports, a common topic at the time. The conversation was light, but it sparked something in Fermi's mind. A little while later, in the middle of lunch, he suddenly blurted out, "But where is everybody?" His lunch companions laughed, but Fermi was serious. He started doing some quick, back-of-the-envelope calculations. The galaxy is very old. It's vast. There are billions of stars, many of them much older than our own sun. There must be billions of planets, and by sheer probability, a significant number should have conditions suitable for life. On some of those, life should have evolved, and on some of those, intelligent life should have developed. A fraction of those should have developed interstellar travel. The logic seems almost undeniable. Our galaxy, the Milky Way, has somewhere between 100 and 400 billion stars. Our Sun is relatively young, about 4.5 billion years old, in a galaxy that's over 13 billion years old. This means that civilizations could have arisen on other planets around other stars billions of years before Earth even formed. Let's think about what that head start means. A civilization just 1,000,000 years more advanced than us, a blink of an eye in cosmic time, would have technology that we would consider magic. Colonizing an entire galaxy seems like a monumental task, but you don't even need faster-than-light travel to do it. Imagine a civilization sends out self-replicating probes, sometimes called von Neumann probes, to nearby star systems. When a probe arrives, it uses local materials, asteroids, dust, whatever it can find, to build a colony and then build copies of itself. Those copies then launch to the next set of star systems. Even traveling at a fraction of the speed of light, this process would spread across the entire galaxy in a surprisingly short amount of time. Depending on the speed and distance between stars, estimates suggest the entire Milky Way could be colonized in as little as 5 million to 50 million years. Again, on a cosmic scale, that's nothing. So, Fermi's question hangs in the air. Given the numbers and the amount of time available, the galaxy should be teeming with life. We should see evidence of it everywhere. We should see megastructures like Dyson spheres built around stars to capture their energy. We should see the waste heat from massive industrial complexes. At the very least, we should be picking up their radio signals, their equivalent of television broadcasts or interplanetary communications spilling out into space. But we see nothing. The sky is silent. This is the heart of the Fermi Paradox, the stark contradiction between the high probability of extraterrestrial intelligence and the complete lack of evidence for it. It's an unsettling, profound mystery. Over the decades, scientists, philosophers, and thinkers have proposed dozens of possible solutions. They generally fall into a few broad categories. The first, and perhaps simplest one, is that intelligent life is just incredibly rare. This is the rare Earth hypothesis. It argues that while simple microbial life might be common, the long chain of events that led to humanity is a fluke of galactic proportions. Maybe the jump from simple prokaryotic cells to complex eukaryotic cells is an evolutionary bottleneck that almost no planet gets through. On Earth, it took over 1.5 billion years to happen. Maybe having a large moon to stabilize our planet's axial tilt is crucial for a stable climate. Maybe having a giant planet like Jupiter in the outer solar system to act as a cosmic vacuum cleaner, sucking up potentially catastrophic asteroids, is a requirement.
The list of potential requirements goes on and on, having plate tectonics to regulate the climate, being in the right part of the galaxy where radiation isn't too intense, having a star of just the right size and stability. If you multiply all these low probabilities together, you might end up with a number so small that Earth is the only planet in the galaxy, or even the observable universe, to have produced a technological civilization. It's a lonely and humbling thought, but it would resolve the paradox neatly.
The second category of solutions is a bit darker. It suggests that intelligent civilizations do exist, but something prevents them from ever making contact. This is the idea of the Great Filter. The Great Filter is some kind of universal barrier or challenge that is extremely difficult for life to overcome. The question is, where is that filter in our timeline? Is it behind us, or is it in front of us? If the filter is behind us, we got lucky. Maybe the origin of life itself was the filter, or maybe it was that jump to complex cells. We passed the test that almost everyone else fails. That would explain why we're seemingly alone. But the more frightening possibility is that the Great Filter is ahead of us. This would mean that intelligent technological civilizations arise fairly often, but they all encounter a barrier that they cannot surpass. What could that be? The answer might be self-destruction. Perhaps any civilization that discovers nuclear power eventually annihilates itself in warfare. Perhaps the development of advanced artificial intelligence inevitably leads to the creators being replaced or destroyed. Or maybe it's environmental collapse. A civilization might inevitably consume its planet's resources and trigger a climate catastrophe before it can become truly spacefaring. If this is true, then the silence we hear in the cosmos is the sound of a graveyard. It's a warning. We might be one of the few civilizations currently alive, but we're approaching the same filter that wiped out all the others. Of course, there are less apocalyptic possibilities within this category. Perhaps interstellar travel is just too difficult or expensive. The energy requirements are immense, and the distances are mind-boggling. Maybe most civilizations conclude it's not worth the effort. They might explore their own solar system and then turn their focus inward, creating virtual realities or focusing on improving life at home. A civilization might not have the expansionist, colonial mindset that we often project onto them. They might be cosmic homebodies. Another idea is that we are simply listening for the wrong things. We've been scanning the skies for radio signals for about 60 years with projects like SETI, the search for extraterrestrial intelligence. That's a tiny window of time, and radio might be a laughably primitive technology for an advanced culture. It's like trying to communicate with someone in a modern city by banging smoke drums. Advanced civilizations might be using something like modulated neutrinos or gravitational waves, or some physics we haven't even discovered yet. Their communications might be all around us, but we lack the senses to perceive them. This leads to a third, even more speculative category of solutions. They are here, or they are aware of us, but they are deliberately staying hidden. This is often called the zoo hypothesis. The idea is that Earth and humanity are part of a cosmic wilderness preserve. More advanced civilizations are observing us, but have a strict non-interference policy, similar to the Prime Directive in Star Trek. They're letting us develop naturally without contamination from outside contact. Perhaps they're waiting for us to reach a certain level of technological or ethical maturity before they reveal themselves. A related idea is that the scale of their intelligence is something we can't even comprehend. The science fiction author Carl Schroeder calls this the first-in problem. The first civilization to achieve superintelligence in the galaxy would have a massive head start. It could have shaped the galaxy to its own ends billions of years ago. Its intelligence might not operate on a level we can recognize. It might be a distributed intelligence in nebulae, or something that exists in other dimensions. It would be to us as we are to an ant. An ant can be standing on the middle of a superhighway, but it has no concept of what a superhighway is or what the cars are. It just experiences vibrations and strange gusts of wind. It's not that the highway is hiding, it's that the ant lacks the conceptual framework to understand what it's experiencing.
Maybe we are in the middle of a galactic civilization, and we are just too primitive to notice.
This whole question forces us to look at something called the Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev. He classified civilizations based on their energy consumption. A Type 1 civilization can harness all the energy available on its home planet. We aren't even there yet. Carl Sagan estimated humanity is around a Type 0.7. A Type 2 civilization can harness all the energy of its host star, likely through a megastructure like a Dyson sphere. A Type 3 civilization can control the energy output of its entire galaxy.
The Fermi Paradox is really a question about the absence of Type 2 and Type 3 civilizations. A Type 3 civilization would be so powerful it would likely alter the shape and appearance of galaxies. We should be able to see their handiwork across the cosmos, but we don't. This suggests that either no one ever reaches that level, or they do so in a way that is invisible to us.
Ultimately, the paradox remains unsolved. It's a perfect problem because it's based on very reasonable assumptions, yet it leads to a conclusion that is contradicted by observation. Each potential solution is fascinating and has profound implications for our understanding of the universe and our place in it.
The silence of the cosmos is like a mirror. It reflects our own hopes and fears. If we are alone, then the flame of consciousness on this tiny planet is a precious, perhaps unique phenomenon in the universe, and we have a profound responsibility to protect it. If we are not alone, then we must ask why we haven't heard from anyone. Are they hiding? Are they extinct? Or are they simply waiting? The silence itself is a message, but we don't yet know how to interpret it.